Hi guys, in the last lecture what we covered is we saw the ratings of transformer and we saw that voltage rating of a transformer was dependent upon the area of the core, current rating was depending upon window area, so it was also directly proportional to area, kVA rating which is equal to voltage rating into current rating was directly proportional to area square which is equal to dimension raised to the power 4. And last one was core loss was proportional to core volume and no load current was proportional to dimension of the core. Okay. Then we saw that if we switch on the transformer when E is equal to 0 and flux is equal to minus phi m, then maximum flux developed was 2 phi m, which is twice the maximum flux. So EMF induced was also 2 EM, which was called as impulse EMF, and the magnetizing current drawn was called as magnetic inrush current, which can damage the winding, insulation, as well as due to forces between the low voltage and the high voltage winding, it can lead to dislocation of winding. That is why proper brassing of the coils is needed if we want to avoid this effect of the inrush current. Okay. In this lecture we will see what happens if we remove the non-ideality or the ideality in the ideal transformer that magnetization curve is linear. In ideal transformer, our last assumption was the magnetization curve of an ideal transformer is linear. If we remove that ideality, then what happens to the operation? So that is called as excitation. Excitation means, what does excitation mean is, excitation means to excite the transformer, that is to develop the flux or the field in case of any transformer. Excitation for any machine just means to develop the field or the flux. To develop the flux. Okay. Like even we'll study in synchronous machines, what happens? A DC source in field winding is kept to excite the machine. Okay. Mostly the field winding in rotating machine is there to excite the machine. So in case of transformer, how will the excitation take place? By means of magnetizing current. Transformer is excited when it draws magnetizing current from the source or when it draws reactive power from the source. As we saw, to develop the flux only reactive power is required. No active power is involved to develop the flux. That will be called as transformer excitation. So now let us consider, if we consider the saturation in the core of the transformer, then what happens to the magnetizing current drawn? So we are assuming that our flux is sinusoidal. If I draw the magnetization characteristics phi versus I mu, then it will be something like this. Due to saturation, it will not be linear. Then if we develop curve between phi and t, as I am telling, flux is sinusoidal. Let us say flux is like this. Now to find the magnetizing current required to develop this flux, what we will do is, we will plot every point like this. For every flux there will be a magnetizing current. Okay, something like this we will plot. So now, based on these values that we are getting on the x-axis, if we plot the magnetizing current versus time, the curve is something like this. Okay. If you see, the peak of the magnetizing current occurs when the flux has the peak. But the shape of the magnetizing current is, this shape is called as peaky because it shows certain peaks. So remember, whenever the flux is sinusoidal, then due to saturation, the magnetizing current drawn by the transformer is peaky in nature. Now we know any periodic waveform, when represented in terms of Fourier series, it can be written like this. It will be I mu 1 sin omega t. This will be called as my fundamental. Then, since this has half wave symmetry, by Fourier series property, I can say it contains only odd harmonics. I mu 3 sin 3 omega t and so on. The most dominant harmonic is third harmonic. Okay. Dominant means the amplitude of third harmonic is highest as compared to other harmonics. So third harmonic is most dominant in the core of the transformer when the magnetizing current being drawn by the transformer is peaky in nature. Okay. So remember this, whenever the flux is sinusoidal, then due to the saturation of the core, the magnetizing current drawn by the core is peaky in nature. That is, it contains a predominant third harmonic. Next, let us consider what happens if we consider the effect of hysteresis. So let us first draw phi versus I mu when we are considering hysteresis. It will be something like this. Next, if we draw phi versus t, I am assuming again that the flux is sinusoidal. Okay. Again, to plot these, we need points on the x-axis. So what happens is, now you see here, when flux is 0, magnetizing current is non-zero. We have two values. Which value to consider is based on whether we are increasing the flux or whether we are decreasing the flux. Okay. So magnetizing current will be non-zero. That means at a time both can never be 0. Whenever the magnetizing current is 0, flux is non-zero. And whenever the flux is 0, magnetizing current is non-zero. Now here in this curve, from here to here, we are increasing the flux. So at 0 flux, I will have this value because this is my increasing curve. In this curve, magnetizing current is increasing as well as flux is increasing. So we will take this value of the magnetizing current when the flux is 0. That is a positive value. So how will the curve look like? The curve will be something like this. Okay. Now the curve will not start from 0 but at a rather leading angle. This angle is called as hysteresis angle. Earlier the peak of both waveforms was aligning, but now the magnetizing current leads the flux by an angle alpha. Alpha is called as the hysteresis angle. Why does this happen? Because due to hysteresis, both flux and the magnetizing current can never be 0 at the same time because the magnetic material will have some retentivity. It will retain some flux in the core. The flux cannot go to 0 as magnetic field or magnetizing current is reduced to 0. That is what we denote by the hysteresis angle. So now there are two types of non-idealities that we have considered so far. First, I have assumed that the transformer core can saturate. The characteristics are nonlinear. What was the effect? That the MMF wave or the magnetizing current wave that was being formed was peaky in nature. Next thing, if we consider hysteresis, then magnetizing current leads the flux by an angle alpha, where alpha is called as hysteresis angle. Next, let us consider the reverse case when we have the sinusoidal magnetizing current and we want to plot the flux. Okay, so first let us draw the saturation characteristics like this. Then let us take that my current is sinusoidal. This is my phi, this is my I mu. If I mu is sinusoidal, how I can draw it? Okay, I can draw it like this. This is my I mu. Okay. Now, if we take each and every point and take the corresponding flux, this value, this value, this value, like this. Now, if we draw the flux waveform, the waveform that comes is something like this. Okay, means it does not show any peak. This waveform is called as flat topped. Okay, means the top of the waveform is flat, it does not have any peak. So what observation can we make is, whenever the magnetizing current drawn by the transformer is sinusoidal in nature, then the flux developed in the transformer core is flat topped. Flat topped means it does not show any peak, it has a flat at the maximum value. Okay. Now, since my flux is flat topped, I need to know what will be the EMF induced, because in the previous case we were considering a sinusoidal flux. That means the derivative of flux will also be sinusoidal. Hence, the EMF induced will also be sinusoidal. But now that my flux is flat topped, I need to know what kind of EMF will be induced. So now that flux is flat topped, let us draw the waveform. How does my flux look like? It is something like this. If we draw the fundamental will be like this. This is my fundamental. In addition, it will have some harmonics since it is non-sinusoidal. If we draw third harmonic, it will be like this. Now if you see, it is being flat topped because the third harmonic is negative here. So it will be subtracted from the fundamental, and that is why we have a valley here. Okay. That means if I want to write down the expression for the flux here, I will write down phi is equal to phi 1 sin omega t plus phi 3 sin 3 omega t plus phi 5 sin 5 omega t and so on. Okay. Because now you can understand why is it flat top, because the value of the third harmonic is coinciding with the peak of the fundamental. That is why it is getting subtracted and my flux is being reduced at the peak and we are getting a flat topped waveform. Now to calculate the EMF, we need to take minus d phi by dt. Okay. So it will be minus, if we take the derivative first of all, phi 1 omega cos omega t plus 3 phi 3 omega cos 3 omega t plus more. Okay, like this it will be there. So if we plot this EMF, then first let us plot the fundamental. Fundamental is minus phi 1 omega cos omega t. It is like this. Then the third harmonic, how it will be? Third harmonic is minus 3 phi 3 omega cos 3 omega t. So it will be like this. It is also minus cosine curve. Now, if you see, the peak of both the waveforms is aligning. That means they will get added up and the resultant EMF, if we draw, it will be something like this. That is, it will be peaky in nature. So if my flux is flat top, then the EMF induced is peaky in nature. So if the flux contains the third harmonic, then the EMF induced will be peaky in nature. So remember what is the flow. If the flux is sinusoidal, EMF will be sinusoidal and magnetizing current will be peaky. If magnetizing current is peaky, flux will be flat topped and EMF will be peaky. Okay. Now the biggest thing is why we are considering the harmonics also. What are the disadvantages or what are the effects of the harmonics? Now suppose current contains harmonics, it will be something like this: I1 sin omega t, I3 sin 3 omega t, plus so on. Now if we calculate RMS value of current, it will be half I1 square plus I3 square plus so on. Now if you see this RMS value is greater than I1 by root 2, if there were no harmonics, the RMS value would be I1 by root 2. So RMS current increases, due to which the losses will also increase, because loss is I RMS square into R. So this will also increase. With increase in RMS current, the copper losses will also increase. So harmonics lead to more losses and lesser efficiency. Also, harmonics lead to electromagnetic interference. Okay, that you will see in power systems, how third harmonic can cause electromagnetic interference with the nearby telephone lines. Actually, we will see in some cases that third harmonic also behaves like a zero sequence current, which can cause interference in the nearby telephone lines, because for a third harmonic, since it behaves as a zero sequence current, the sum of currents will not be zero. Okay, so these are some of the disadvantages that we possess with the harmonics. So harmonics are undesirable in the system. They make a waveform non-sinusoidal and deviate from its ideal behavior. So let us summarize what we have learnt in this lecture. First we saw flux is sinusoidal, then I mu is peaky and it leads by hysteresis angle. Due to sinusoidal flux, EMF is sinusoidal. Okay, then if I mu is sinusoidal, what happens? Flux is flat topped and EMF is peaky. Okay, so this is what we saw in this lecture. So remember this is important from theoretical point of view. 1 mark question can be directly asked: what will be the nature of flux or what will be the nature of the magnetizing current? But mostly it has very less chances of coming in gate examination. It used to come long before, but now this may appear in most of the PSU examinations or even the engineering services examination. Okay, in the next lecture we will see some problems based on single phase transformer, so that you get clarity in how to apply these concepts that we have learned so far.